Hey there, welcome to another episode of GeoNoding Adventures, a series where I go through the process of creating something with geometry nodes, from idea to final product. So let's go on a journey to create something cool. A while ago, I was doing some afternoon noodling, and I realized that I haven't tried combining the Extrude Mesh node with the Subdivision Surface node yet. The Extrude Mesh node alone is arguably one of the more powerful nodes when it comes to creating cool shapes and abstract meshes. So I assumed that adding a Subdivision Surface node to the mix would create a whole new level of possibilities. And it would also make the GeoNoding process somewhat more similar to the process of regular modeling. Usually when you're doing regular modeling, unless you're doing sculpting, your workflow will fall into one of two camps: hard surface modeling or subdivision surface modeling. The hard surface modeling workflow is pretty straightforward, but it's hard to master. Essentially, you turn on Auto Smooth, add a bevel modifier to your mesh, and then use a multitude of so-called cutter objects, which are objects used in combination with a Boolean modifier to create the final mesh. One of the main benefits of this workflow is that it's non-destructive, meaning that you at any time can revert or modify any modification by removing or modifying the cutter objects. The polar opposite of hard surface modeling is subdivision surface modeling. The workflow here is that you add a subdivision surface modifier and then modify the mesh by making extrusions and loop cuts. This technique is extremely powerful if you learn how to use it properly, and you can create pretty much anything with it. The downside, of course, is that this workflow is destructive, so if you make a modification that you later don't want, you will have to do some work to revert it. So with this information in mind, I was thinking about what would be a good project for doing the equivalent of subdivision surface modeling with geometry nodes. And fairly quickly I decided that some sort of tentacle would be a good one, for one simple reason. You see, one aspect to keep in mind when using a subdivision surface modifier is that it turns squares to circles, and of course rectangles to ellipses, and the same is true when using the subdivision surface node. This means that whatever face that I extrude with the extrude mesh node will become circular by default, which is perfect for creating something like the suction cups of an octopus tentacle. First, I decided to create a completely smooth tentacle to use as the base. Doing this in geometry node is extremely simple. All you need is a curve line, a curve to mesh node, and a curve circle as the profile curve. You can then use a set curve radius node with the factor of the Spline Parameter node as the radius. Then you can just reverse the radius with the float curve node. Sure, it looks more like a cone, but this setup is a good base for two reasons. Reason 1, the resolution of the profile can be adjusted with the resolution of the curve circle, and since I'm trying to emulate subdivision surface modeling, I want to keep the mesh fairly low poly. And reason 2, since I'm using a curve as the base, I can also very easily adjust the resolution of the curve itself with the resample curve node. A neat side effect of using a float curve node to reverse the spline factor is that it can be used to create sort of a custom falloff. Or even a completely custom profile. At this point, I started creating some extrusions while thinking about how I would have done it if I was doing regular modeling. Creating a version of the extrusions using regular modeling first can be a good way to more easily get a feeling for how you can approach your extrusions in a node tree. For example, first I would inset the face so that the base of the cup doesn't cover the entire face. Then I would extrude the inset face straight up to create the base of the cup. I would then inset the top face again to create the perimeter of the cup itself. And finally, I would extrude the inset face downwards and scale it down a bit. Another perk of doing it manually like this is that you can get a good visualization of what it will look like once you add the Subdivision Surface node. Now, there isn't an inset node, but you can get the same effect by setting the extrusion offset scale to 0, and then scaling down the top face with the Scale Elements node. So from here it was just a matter of following the extrusion flow to create the suction cups. And then adding a Subdivision Surface node. Cool, I thought. But that's not looking too good. And while I was looking at it, I realized that it made sense, since the extrusions are using the same values for every face. A more reasonable look would be if the length of the extrusions gets shorter the further up along the tentacle they were located. And I figured that I could use the same approach that I used for the curve radius to achieve what I was after. However, when I tried using the Spline Parameter factor like before, it didn't work. This confused me at first, but after giving it some thought I realized what was going on. You see, since not even multiplying the factor with huge values had any effect at all, it means that the values of the factor must be 0. But when I looked at what the factor values are after resampling, they are very obviously going from 0 to 1. However, when I looked at the factor values after the conversion to a mesh, those values were indeed all 0. So why is the factor outputting a gradient from 0 to 1 over here, but not over here? Well, it has to do with how the field system works. Essentially, any socket that is shaped like a diamond is using fields to evaluate values. The field system is a huge topic on its own, so if you want to know more about it, I recommend that you watch this video by Erindale. But in short, the system evaluates values depending on the context that those values are accessed in. When I use the factor here in the set curve radius node, the context is the connected geometry, which at this point in the node tree is the resampled curve. When I use the factor over here in the extrude mesh node, the context is again the connected geometry. However, at this point, that geometry is no longer a curve, but instead a mesh. And since the curve is non-existing, the factor defaults to 0. Catastrophic, right? Well, no, because there are ways to transfer, or capture, attributes from previous points in the node tree that can be used at later points. So for example here, I want to use the spline parameter from after the resampling, and I can do that by using a capture attribute node with the spline parameter factor as the value. Then I just have to adjust the falloff with the float curve node like before. And multiplying the resulting value with some smaller value to get a good look. And of course, I have to do the same for some of the other extrusions as well. Now I wanted to add some shading to it, so I created a material, added a set material node, and selected the material. One trick that I like to use when working with geometry nodes is to use an Ambient Occlusion node to automatically create gradients. One benefit of using this technique is that it doesn't require a UV map, since the gradients are completely dependent on the geometry itself. Mesh primitives in a node tree like cubes and spheres do have UV maps that can be accessed in the shader. But when you create custom meshes, for example by converting a curve to a mesh, there is no UV map available. However, it's possible to create texture coordinates in a node tree on your own, and use that as a substitute for a UV map in the shader. If you want a detailed explanation of how it works, you can watch this video by Bradley Animation. But essentially, we can use the factor of the original curve as the x-coordinate, and the factor of the profile curve as a y-coordinate in a combined XYZ node. This custom coordinate can then be used as a custom output of the node tree. And accessed in the shader with an attribute node. This works pretty well on a smooth curve mesh like this. But not so well after we add extrusions to it. But no worries, we can just take some artistic liberties and use it in a way that looks, well, half decent at least. I was pretty happy with how it was turning out, so started thinking of ways to make it move and squirm around like an actual tentacle. I knew that using a set position node on the curve with some sort of noise texture as the offset is probably the most straightforward way to do it, so I used that as the base. This presented two new problems though. Firstly, when you're using noise textures as the offset, it also moves the entire mesh 0.5 units on all axes, because the noise outputs values from 0 to 1 that gets averaged out to 0.5. To get around this issue, it's just a matter of subtracting 0.5 on all axes before using it as the offset value. Secondly, now that the curve is being distorted, it looks really blocky. The reason for this is that by default, the curve is of the type poly, which essentially behaves like a regular mesh. So to get around this issue, we can change the curve type with the Set Spline Type node set to Bezier. And then use a Set Handle type set to Auto to properly smooth the curve. I'm not entirely sure why, but doing this seems to subdivide the curve for some reason. Though according to the spreadsheet, nothing has changed. It might be a bug or maybe I'm misunderstanding something. Either way, the fix to this is to just resample the curve again after the set position node. I then used a scene time node to get the current frame of the timeline and divided it with a larger value. And I then used the resulting value as the W value of the noise texture. I thought it looked pretty cool and gross, but I figured that it would look more natural if the movement was more prevalent at the top than at the bottom. To achieve this, I again used the Spline Parameter factor to multiply the noise in order to get the gradient falloff. And I then multiplied that value again to amplify the movement. As a final touch, I wanted to make it so that the tentacle only has 2 rows of suction cups. Luckily, the same selection socket that I used to specify which faces to extrude can be used to select specific faces on the mesh before making the first extrusion. I wasn't sure exactly in what order the indices of the faces were, but I suspected that they were ordered in a circular fashion like this, where the bottom row of faces go from 0 to 5, since the resolution of the curve profile is set to 6, with the next row after that going from 6 to 11, and so on. I decided to test my hypothesis by taking the index of each face with the capture attribute node, set to integer and face, and run them through a modular node with the mod value being the resolution of the profile curve. I can then use the resulting value in combination with the compare node set to less than to create a selection where the B value will represent the amount of rows of suction cups. At this point I was pretty satisfied with the result, and I left it at that for a day or two. But then I remembered seeing a video by Default Cube, where he showed that it's possible to use geometry nodes to add geometry to a softbody simulation of a simple curve, which results in extremely lightweight simulations, since Blender only has to simulate the curve instead of a highly detailed mesh. I also remembered seeing a video by Nicolas Rouelle, where they used tentacles with a cloth animation to control them with forces, which made the tentacles wrap around objects and themselves. So naturally, I had to try a combination of these techniques with my procedural tentacle, in hopes of getting some cool results. First, I needed to create a simple softbody simulation. I could use a curve for this, but in order to be able to do things like locking certain parts of the simulation in place, I need to be able to use vertex groups. So I used a plane and merged it on the x-axis to get a line. And I then subdivided it a couple of times to get some more geometry. And I then assigned the bottom two vertices to a vertex group. I then added a softbody to the mesh and set the vertex groups as the goal group. And maxed both the stiffness and strengths so that those vertices stay in place. I also enabled self-collision and set the gravity to 0 in the field weights so that the mesh isn't affected by it. And set end frame of the cache to 1000 along with the timeline to get a longer simulation. And finally, I added a force object. By default, the strength is set to 1, which creates an outward force with a strength of 1. But for my purposes, I wanted an inward force that pulls the tentacles towards it, so I set the strength to a negative number instead. Looks good, but I think I need a floor as well, and I guess a plane with collision will do. Now I just needed to modify the node tree to use the input geometry instead of a curve created within it. Since the input geometry is a mesh, I also need to convert it to a curve before resampling it. Also, I figured that I probably should decrease the movement from the noise texture by a fair amount, since the main movement will be generated by the force object. So all that was left to do at this point was to press play and see what happens. It's not perfect, but I'm actually surprised at how organic it looks. So naturally, I had to add some more. And some collision objects. The biggest issue with this approach is that the collisions are handled before the actual mesh is generated, and this can result in some clipping from time to time. Another issue is that while the softbody has an internal self-collision radius that can be adjusted with the bolt size under self-collision, the collisions between different softbody objects and collision objects are not affected by this. A way to mitigate this for other softbody objects is to add more mesh lines in one object in edit mode instead of having them as separate objects. However, this quickly becomes very computationally heavy. Anyway, I felt like this was a good place to leave the project at, and overall, I was pleased with what it had turned into. And most importantly, it was extremely fun to play around with. So thanks for joining me on this GeoNoding adventure. I hope the journey was interesting and that you learned something new. See you next time.